Okay, so now we want to formalize this idea of what we call complex conjugates. And this word conjugates here, we've actually seen before. Where have we seen it? Well, when we've looked at binomial expansions, right? We knew that if I had a question like this, 1 over root 2 minus 1, for example, I could find the conjugate, which was essentially just changing the subtraction sign into an addition sign. And what did that allow us to do? Well, it allowed us to rationalize the denominator, right? So I could write this with a rational denominator, and that guy is going to be the difference of 2 squares, so I'll get 2 minus 1, and that'll be nice, that's just root 2 plus 1. All right, so that's what the conjugates allowed us to do for real numbers. With our complex numbers, we're going to try and achieve a similar thing later on when we look at something called realizing the denominator, which I guess that's a bit of a clue for what you need to be able to do. But with our complex conjugates, there's a bit more of a formal definition. With our real numbers, we just kind of said, you just change the sign, and that allows you to do that. But for a complex number, if I have z is equal to x plus iy, for example, yi, if I want to find the conjugate, and we represent this with a bar on top, right, that's the conjugate, what we actually do is we change the sign of the imaginary part. So I'm going to get x minus yi here, okay? So in other words, we're just changing the sign of the imaginary part there. Okay, so what does this allow us to do? Well, if I have a question like this, right, what do I do here? Well, if I want to find the conjugate of something like this, all I do is, okay, which is the imaginary part? Well, I can see that this is my imaginary part here, so the conjugate of 7 plus I is just going to be 7 minus I. Not too bad, right? It doesn't matter what kind of values we have. If I had something like this, potentially, right, what would this guy be? Well, I see, all right, the real part, that stays the same. That's going to be negative 5. But for my imaginary part now, I'm just going to change the sign so it's a positive 2i. Right? So far, so good. What happens if I give you this guy? Conjugate of 9. Now, like I said, we changed the sign of the imaginary part, but I mean, what is the imaginary part here? Really, if you think about it, another way you can write this is 9 plus 0i. And I suppose you can change the sign here, but nothing's going to change in terms of its value, right? If you did do that, it would just be 9 minus 0i, which is still just 9. So the complex conjugate of 9 is still 9 there. So just something kind of interesting to note. All right, so what can we kind of do with these? Well, there's actually a whole suite of identities and properties that we can actually work with when we do operations with the conjugates. And it is good to be familiar with them. And you may even want to memorize them, but it is also very important to know how they're derived and to be able to work with these complex conjugates. Let me give you 2 examples of these. So here's our first one. So here's one interesting identity, right? So if we do z plus the conjugate of z, you're going to get 2 times the real part of z. How are we going to prove that? Well, what we first need to do is we need to introduce our complex number. So let z equal to x plus yi, right? And so then I say, okay, well, I've got z. What would its conjugate be? Well, that means its conjugate would be x minus yi, right? So we say, all right, therefore, let's take the left-hand side of this, because anytime with a proof, we want to kind of work from one side to the other generally, which makes it a good structure. So I'm going to do z plus z conjugate. And so I've got x plus yi plus x minus yi. And you see something interesting going on here. Well, what's going to happen to these yi's? They're just going to cancel out. And so I get left with 2x, which is equal to 2 times the real part of z, because what is the real part of z? It's just x over here, that's the real part. So it equals 2 times the real part of z, which is the right-hand side. And you can kind of see why that's happening, right? Because essentially, if you are adding a complex number with its conjugate, right, all you're doing is you're changing the sign here for the conjugate, and if you add these together, these imaginary parts will always cancel through. Okay, so far so good. Now, what about a little trickier one? Do I do this one? Let's give it a go. Okay, here's our next example. Prove that the conjugate of z on w is the same as the conjugate of z divided by the conjugate of w. Now for something like this, just at first glance, it may seem like this is something that should be kind of obvious, right? But the key thing is to never take anything for granted. We want to be able to show this. So how can we start with it? Well, let's take a similar proof structure. Let's take a left-hand side and see if we can arrive at something, potentially arrive at what this would be. Really, they should be saying in a question like this that z and w are complex numbers, they belong to the complex set there. And if we do have that, then we can let z equal to, for example, a plus bi, and w equal to c plus di. And if you want to, you can make it clear that a, b, c, and d, these are all real numbers, right? So what are we going to do here? Well, if I want to take the left-hand side, right, what do I need to do? I need to find the conjugate of a plus bi over c plus di here, because that's z on w. The issue is when we looked at division, right, well, how do we define division? What we said was, well, actually, I don't know how to just kind of take the operations here. What I have to do is I have to realize the denominator, which is why we introduced the complex conjugate in the first place, because it allows me to define division, essentially, for complex numbers, right? So let's go ahead and do that. So it's going to be the conjugate of, this is going to get pretty long. So we've got a plus bi over c plus di multiplied by c minus di over c minus di, okay? Don't forget that we're taking the conjugate this whole thing at the end as well. This guy over here, we've got our brackets like so. And then we have an identity that makes it easy for us. This is just going to be the sum of two squares. So it's just c squared plus d squared. If you're not too sure how that works, right, if I get some more room, potentially. This expansion on the bottom, c plus di, c minus di, we can expand this out and we'll get c squared plus di minus, plus cdi minus cdi minus di squared. And so these cancel out, and then I squared is -1 here, so that's just c squared plus d squared, right? But the sum of two squares is a bit of a shortcut you can take. So far so good. Oh, sorry, I left off the conjugate there. And see, the problem is when you have it in this form, it's not immediately obvious what the conjugate is. You don't have it in that real and imaginary part separated out. So what you need to do is you actually need to expand this out here. We've got AC minus ADI plus BCI minus BDI squared all over C squared plus D squared. Sorry, it's getting confusing with all these bars and conjugates. So that's the conjugate. And I'll do it in a different color. Yeah, sure. And we keep going over here. Plus BCI. All over C squared plus D squared. And one last step I want to do, I'm actually going to factorize out the I here so I can really see the imaginary and real parts. So here's my real part, AC plus BD. And if I factorize out I, I'm going to get BC minus AD and then so now I can take the conjugate after that manipulation. That will be AC plus BD minus I BC minus AD. Okay, half of it down. What's the other half? So that's what left-hand side is. So now the goal would be to find what the right-hand side is. So let's go ahead and do that. So my right-hand side is going to be equal to Z conjugate on W conjugate. So A minus BI on C minus DI. Yeah, I should plus, I don't know why I rubbed off. And again, we haven't defined division. Well, we have defined division. What we have to do is we have to realize the denominator. So c plus di multiplied by c plus di. And we can go ahead and expand this out. Which is, again, this is looking slightly familiar, although slightly different, right? On the denominator, we still have the sum of two squares. But this bracket looks slightly different from what we had before, but you'll notice that we had the conjugate here. So let's expand this out and see what happens, right? So I'm going to get, again, AC plus ADI minus BCI minus BDI squared all over C squared plus D squared. And let's just do a bit of arranging. So I have the real and imaginary parts to compare. So I've got AC minus BDI squared, but here's I squared is my negative 1. So that's going to just be AC plus BD. That's my real part. And then again, I've got plus ADI minus BCI all over C squared plus D squared. And just one last step, I'm going to factorize out my I. So I end up with, well, the thing is, I want to show that I have this here, right? Negative I outside of BC minus AD. So rather than factorizing out positive I, if I factorize out negative I here, and I just swap the signs of both of these terms, I do end up with BC minus AD there, all over C squared plus D squared, which is equal to LHS, I suppose, right? Or we could say, therefore, LHS is equal to RHS. So fairly extensive proof. Not a short one by any means, but can you see the power of our complex conjugates is in being able to prove identities like this, combining with our definitions of division. Okay, so that's a proof question from complex numbers and conjugates.